Alright, so chapter 7 is all about a new type of function called an exponential function. We want to talk about a couple things in section 7.1. In particular, most sections have a part about how to graph these functions because it's nice to see visually what it looks like. So in this section we'll talk about two major functions, exponential growth, and those curves look roughly like this. They're growing, and then decay, which would look like this, something going down. And what's interesting about these functions is a lot of real-life scenarios are simulated or modeled by exponential functions. Just to give you kind of a comparison between a function that we already know, a quadratic function, so x squared, that's on the left side, and then an exponential function like 2 to the x, I want to show you kind of a comparison about what happens. So let's plug in x equals 2 first. And you can see this will be 2 squared, which is 4. This will also be 2 to the second, which is 4. So they start out kind of similar. Let's try x equals 3. In that case, we'd have 3 squared, which is 9. And this will be 2 to the third, which is 8. So far, it looks like they're pretty even. But the thing that's noteworthy about exponentials is they grow at an incredibly fast rate. So if you plug in x to the 10th, this becomes 10 squared, which is 100. And this one right here becomes 2 to the 10th, which is 1,024. Okay, let's just see one more, x to the 20th, or sorry, x equals 20, I should say. That's 20 squared, 20 times 20, which is 400. Okay, this one right here is 2 to the 20th power, which is an enormous number. I believe that is 1,048,576. So what you can see happening is these functions get enormously large very quickly. Okay, and just to give you a visual of that, here's what the graph of x squared looks like. And then if you graph 2 to the x next to it, you can see the blue line is kind of similar to it in this region, but then let's zoom out a little bit and you can see, not a great picture, but you can see how quickly the blue line starts rising. I mean, way up here we're at 300, the x squared graph takes a much longer to get out there. It's incredibly steep how it gets very quickly, that exponent curve. Okay, so that's the main thing. Exponential functions grow at a very fast rate. Okay, here's just some of the information on what they look like. Exponential growth. So here's the general form of an exponential. If this number is bigger than 1, that's what they say here. If that number is bigger than 1, you have exponential growth. So 2 to the x, 3 to the x, 4 to the x, any of these numbers, 1.1 to the x, all of these numbers, those are called the base numbers. All of them are bigger than 1, so they all represent growth. Okay, the domain on a graph is all real numbers. X goes forever this direction, it goes forever this direction. Notice that down here it never actually touches 0, it never goes negative, and that's why the range is all positive numbers. Y is never less than 0. Why not? Well, let's take this function right here, like 2 to the x. Suppose you plug in a huge negative number like that. You might remember from earlier that negative exponents, the way that we simplify it is to flip it to the bottom and make it positive. And this number here is huge. When you put that in a calculator, it's going to be very, very close to 0. It would be like 0, 0, 0, goes way out here. You might finally reach a 1. That's super close to 0, but it never actually reaches 0. And the name for that, when you get really close to something without ever touching it, the name for that is called an asymptote. And in this example, the asymptote is y equals 0. This purple line right here gets super close to 0. It gets like 0.000000, really close, but it never touches. Okay, this is the other important thing. The y-intercept is 0, 1, and here's y. If you plug in 0 for x to any of these functions, actually if you plug in 0 here or here or here, anything to the 0 is equal to 1. So that is why the point 0, x equals 0, comma y equals 1 is on that graph. It's on any exponential graph. Alright, so we'll graph this and then we will state the domain and the range. The easiest way to do it is to make a table of values, which we have kind of set up here. And I'll just draw it a little bit different here so we can see it better. And usually you really only need a couple points here. I always start by seeing what would make that 0, and in this case 0 would make that 0. 3 to the 0 is equal to 1, so the point 0, comma 1 is on this graph. And then let's just do 2 more that are bigger, and we'll do 2 more that are smaller. So 3 to the first power is 3, 3 to the second power is 9, so the points 1, comma 3 and 2, comma 9 will be on this graph, and you can see how steeply that's going to go up. And then 3 to the negative 1 is like 1 over 3 to the positive 1, so 1/3. So -1 comma 1/3 is about here, and 3 to the -2 is 1 over 3 to the +2, or 1 over 9. So -2 comma 1/9 is about right here, and you can see it's going to get really, really close to 0, but it never actually touches. That's an asymptote. Okay, the domain for all exponentials is all real numbers, and in this case the range is y is greater than or equal to 0, because it never goes below the x-axis. So I would recommend, when you're doing these, make a table of values where the middle number is what makes the exponent part 0, and then a couple numbers bigger and a couple numbers smaller, and then you connect the dots. Okay, the transformation rules that we've talked about with other graphs are the exact same for exponentials. So let's just plug in an actual example here. Let's say y is equal to, let's do this. We'll do -2 times 3 to the x minus 1 plus 4. Okay, this is going to do 4 different things. And you might remember the acronym add to x, go left, add to x, go left, and then add to y, go high. Okay, so this right here is going to move it right and left because it's attached to the x, and the x direction on the axis, x-axis, is the right and left axis. And since adding to x makes it go left, subtracting from x is going to make it go right. So that means go right 1. This number here will vertically stretch it by a factor of 2, which means it will horizontally shrink it, because vertical and horizontal do opposite things. This is going to reflect over the x-axis, and I'll show you a picture of this in just a second. And finally, add to y, go high, so that's going to go up 4. So what we'll do is we'll graph the parent function of this. The parent function will be y equals 3 to the x, and then you can see that purple one is when we've changed around y equals 3 to the x. So let's first graph 3 to the x, which looks like that. Oops. Gonna move down for a second here and zoom in. Okay, so that is roughly what we get right there. That's what the picture looks like. And now let's graph the transformation. So, sorry. Here we go. So let's start with 3 to the x minus 1. So that should shift it to the right 1. So let's verify that. So you can see, oops, get this to work, x minus 1, close parentheses. Okay, so you can see the red one has been shifted to the right 1. Then let's put a 2 in front of it. So 2 times that. So you can see it kind of stretched that out a little bit. And then the negative should reflect it. So let's put a negative in front of it. There, it just got reflected. And then the plus 4 should make it shift up 4, and it did. So you can see how those transformations work. Okay, why is this useful? Because it helps us be able to graph our functions based on what the parent function should look like. So let's do this. And the easiest way to do this, this particular one, if we look at, that's going to be 2 to the x plus 1. That's just going to take 2 to the x, and it's going to bump it up 1. So let's just graph y equals 2 to the x first, and then we can easily be able to transform it from there. They're not always easy to transform just by sight, but this one will be. So 2 to the 0, that would be 1. So the point 0, 1 is on this parent function graph. 2 to the 1 is 2. 2 to the 2 is 4. So let's just graph those points. The next point is 1 comma 2. So that puts us here. This one is x equals 2, y equals 4. So that puts us here. 2 to the negative 1 is 1 over 2 to the positive 1. So that's going to be the point -1 comma 1/2. And then this one here, 2 to the negative 2, is 1 over 2 to the positive 2. So that is this point right here, -2 comma 1/4, and that's about here. So this red function is the graph y equals 2 to the x. What will the other one look like? We'll do this in different color. Well, notice this is just going to take this graph right here and just bump everything up 1. So if we add 1 to that coordinate, we get 2. If we add 1 to this coordinate, we get 3. This one would become 5. This one would be 1.5. This one would be 1 1/4. Right? So let's just graph all of these points. We'll just literally bump them up a single spot, and that will give us our graph. So it looks like that blue graph right there, same graph, just been transformed by going a direction of up 1 to the x, and then that's a big +1. Alright, this one's a little bit trickier because now we have a bunch of transformations, so this one would not be easy to do by sight. So the easiest way to do this one would be to actually graph the parent function right here, and then next to it we'll graph the new one. Okay, so to get a nice picture we need usually just a couple points, 0, and then we'll do 1 and 2, -1, -2. So 5 to the 0 is equal to 1, 5 to the 1 equals 5, 5 to the 2 equals 25, 5 to the -1 equals 1 over 5, and 5 to the -2 equals 1 over 5 to the +2, or 1 over 25. So we'll graph these points just so we can see what the parent function looks like. So there's 0, 1, 1, 5 is here, 2, 25 is not even going to fit, it's way up there, so that's not drawn to scale. -1, 1/5 is about here, -2, 25th is about there. So we at least get a reasonably good picture. That's a really steep rise right there. Okay, and then let's see what the parent function is going to look like. It's basically going to take this original function, oops, it's supposed to be a -1/2. It's going to take this original function and it will do a couple things to it. So this is going to make it move right 2. This is going to vertically shrink it by a half because it's less than 1. If it was greater than 1, you stretch it, and that's going to reflect over the axis, over the x-axis. Okay, so now the question is, what should go in the center of the graph? Well, actually 2 is what's going to make that value equal to 0. So we'll start there. -1/2 times 5 to the 2 minus 2, that's 5 to the 0, which is 1, and 1 times -1/2 is -1/2. So the point 2, -1/2 is about right here. Okay, remember that we're taking this and kind of shifting it to the right. This graph right here is going to be 5 to the, we'll plug in 1. So -1/2 times 5 to the -1, and that's the same as 1 over 5 to the +1. So that's the same as -1/10. So the point 1, -1/10 is about right here. And then let's get some points in the other direction because these fractions are going to get increasingly small. We're going from -1/2 to -1/10. The next one's going to be even smaller. It's going to be, let's just find it for the sake of having it. So if you plug in 0 right here, 0 minus 2 would be -2. So you get -1/2 times 1 over 5 to the 2, or 1 over 25. That's a positive 1 over 25. So that's -1/50th. -1/50th, that's so small you can hardly draw it. It's about that little tiny dot right there. And then let's get a point going the other way. So we're going to have -1/2 times, if we plug in 3 for x, 3 minus 2 is 1. So we have -5 over 2, -2.5. So 3, -2.5 is about there. And you can see that that roughly does what we said it was going to do. It's flipped over the x-axis, it's been shifted 2 to the right, and it's been kind of somehow vertically shrunk down. It's a little bit hard to see it on the hand-drawn graphs, but you can get a good picture on a graphing calculator also. Alright, so sometimes they might give you a graph and say write the equation for it. Okay, so here is the equation for our graph. And it's harder to do this with other types of transformations. We're just going to stick with the basic kind where you have a base b and a multiplier a in front of it. So easiest way to do this would be to find this point, find the y-intercept, and that looks like that's at the point 0, 1/2. And then find a point that's right on the intersection of those circles, or it's not the circles, sorry, the squares. That's right, it's very clear what that point is, it's 2, 2. So we just need to plug those in. To find A, and A is this number right here. To find A, we start by plugging in x equals 0, and you'll see why. Here's the point we want to plug in, so y equals 1/2, and x is equal to 0. Why do we do that? Because b to the 0 equals 1, so that's the same as 1/2 is equal to 1 times a, or 1/2 equals a. So now we can, I'll just put the answer up here, different color. We have y equals 1/2 times, and we still don't know what b is. That's the next task we have to do. Okay, so to find b, we will plug in our other point on that graph. So we really only need 2 points to do this. And we have another point, we have 2, 2 right here, so we'll plug in y equals 2. We now know that a is 1/2, we know that, we don't know b yet, so I'm going to leave that blank. We know x is 2, because we're taking this point right here. So let's divide this by 1/2, And over here, dividing by 1/2 is like multiplying by 2. So we get 4 is equal to b squared. If we square root both sides, we would get b is equal to 2. Not negative 2, the negative would come out front. So b equals to 2. So now our function or our equation is this right here. Y equals 1/2 times 2 to the x. 2 is a number bigger than 1, so that means it's exponential growth, and that agrees with what the picture is. So there's the answer. Alright, let's do another one. Now, we notice right away this should be exponential decay, because this line is kind of going down as you go from left to right. Okay, so let's start by finding our 2 points. That's the point right there, 0, 4. So let's plug that in. 4 equals a times b to the 0. Anything to the 0 is 1. So 4 equals a times 1, or 4 equals a. So at least we have the a part of that. We have 4 times, we don't know, b to the x. And we need a second point. It looks like this is another point right there. That's the point 1, 2. So we'll plug in 2 for y. We know that a is 4. We don't know b, but we know x is 1. So we'll divide this by 4. We'll divide this by 4. We get b is equal to 2 over 4, or 1/2. And that must be our equation, and that agrees with what we said, because we said this is exponential decay, and 1/2 is less than 1. And when the number that you're raising to the x is less than 1, it represents decay. So there it is. Actually, they just wrote it a little bit different. They wrote it with the x outside, so I'll do that as well. So there's our function. Okay, this is used, like I said, in many cases in real life. So one of the best examples would be with money. That function right there is related to the compound interest function. So what all this stuff means, this means the initial amount. Like for example, with money, it would be what you're investing. This represents the rate of growth, and t represents time. Okay, and then this number right here is called the growth factor, because if r is bigger than, it basically tells you like how much money you're going to make. For example, I think of money in terms of this. This is the compound interest formula for money. This is called simple interest. That's just if your money is not compounding. We'll talk more about that. And another time this is used is to talk about population growth, and we'll probably see some examples like that as well. If not in this section, then in another one. Alright, so let's take a look. I've already graphed this function on Desmos, but I haven't shown you the equation yet, so we'll do that equation right now. So remember, that equation we were just talking about is this right here. And what this is, we said population is another case when you use it. This is showing the population from the U.S. Census from that year to basically today. Shows you has grown by 2.03%. So remember, r in this equation is the rate. And we don't want to keep it as a percent. We want to change that to a decimal. So just to recall how you change percents to a decimal, you move the decimal 2 places to the left. And the reason you move it 2 places to the left is percent actually means over 100. So it's like I'm taking 2.03 and I'm dividing by 100. How do you divide something by 100? You move the decimal twice, because there's 2 zeros in 100. So that is going to be the number. If we move it twice, we fill that in. It's going to be 0.0203. So let's start filling this in. So this is going to be 1 plus 0.0203, and we could just make that 1.0203. Now again, that's going to be exponential growth, because this number here is bigger than 1. And that's how you tell if the number in that you're raising to the t is bigger than 1, it's growth. If it's less than 1, it would be decay. And then what is A? A is the initial, this A right here, not the big A. A is the initial amount. So if we look at this equation, they're telling us the initial population was that number. So therefore that is our A. So I'll put that in right here. It's supposed to go right here too, but I can't fit it. So 3,929,214 is the initial population of the United States. And it grows by that amount. So what's nice about this is now we can predict what the population could be at any given time. So in 1790, that was 227 years ago. If you plug in the number 227 here, out of curiosity, let's just do that and see what we get. So we're going to plug in 3 million. This will give us a rough prediction of our current population. So let's see that. So 3,929,214 parentheses times this growth rate. put the parentheses so the calculator doesn't get confused by the order of operations. And then we'll raise it to the x, because x and t mean the same thing. Actually, we're going to raise it to the 227, because that's the number of years after 1790. And we get this huge number here, 376 million. So it's a little bit off because our current population is about 320 million, but it's still a decent predictor. Okay, exponential decay, like we said, very similar. Only difference really from exponential growth, the domain is the same, the range is the same, asymptote is the same. The only difference is this number here is between 0 and 1. It's like a fraction or a decimal usually, like 0.2 or 0.5. So for example, this right here, that is exponential decay. This right here is exponential decay. This right here is not exponential decay because 1.3 is bigger than 1. So that would be growth. Okay, so in terms of how we graph this, we do it the exact same way. Y equals 1/3 to the x. Just see, let's do a slightly more complicated version here because we kind of did this already. You would take a table of values and plug in those numbers that you see, but this one's a little bit more interesting. And actually for these types of problems, I would really recommend using a graphing calculator simply because it's a little bit, in general, when you do these problems, you would be using graphing calculators because most of these numbers are not easy to find. But I'll show you how to do one by hand. So this is going to take the graph and we'll move it right to, it's going to be decay because of the 1/4. It will stretch it vertically by a factor of 2. Vertically stretch, which means horizontally shrink, and then this right here is going to move it down 3. So let's just pick a couple points in here. The number that should go in the middle is whatever makes this equal to 0, and -2 for x would make that 0. So we'd have 2 times 1/4 to the 0 minus 3. Anything to the 0 is 1, so that's 2 times 1, which is 2, minus 3 is -1. So -2, -1 is on our graph. Then let's do a couple points bigger and a couple points smaller. Okay, so let's start with -1. So 2 times 1/4 to the, if we plug in -1, that would be raised to the 1. So 2 times a fourth is a half, and a half minus 3 would be -2.5. So that's going to be the point, -1, -2.5, which is right here. This should be going down, and it looks like already that it is going to be going down. And then finally, let's plug in this right here. 0 plugged in for x would be 0 plus 2. 1/4 squared is 1/16, times 2 would be 1/8, and 1/8 minus 3 is going to be -2.875. So 0, -2.875 puts us about right here. Is that going to be right? Yes, looks like it is right. It should be going down, and it is. Okay, this one, get maybe one more point should be good. So -3 plus 2 would be -1. Just want to show you how this looks. So 2 times 1/4 to the -1. Well, that means we should flip it and make it positive. So if we flip 1/4, we would get 4. That's going to be 2 times 4 to the first power. Minus 3. That turns out to be 5. So the point -3, 5 is on our graph, and you can see it's going to start dropping pretty steeply. So it's, oops, I shouldn't have gone past -3 because -3 is the asymptote. And how do we know it was going to be -3? Because this whole thing right here, I mean, you can see this -3 drops it from its normal asymptote. It basically shifts it from 0 down 3, and then it rises up steeply like that. So that is roughly how the graph looks. The range would be anything where y is greater than that. So y is greater than or equal to -3. The domain is always all real numbers. Alright, the last thing I want to show you is how the equation looks for decay. It's the same as the other one. The only difference is this part. Instead of 1 plus r, it's 1 minus r. And that's called not the growth factor, but the decay factor. Alright, so they have this problem here on the amount of caffeine that decays from people's systems after, or per hour, basically. So we want to draw a graph, and before we can draw the graph, we need to know what the equation is, obviously. So here's our equation. T is going to remain in this equation. This number right here is the decay factor. So if we change that to a decimal, we'll move the decimal 2 places, so 1, 2, so we get 0.125. So basically it means that if 12.5% is leaving your body every hour, then how much percent is left? It would be 87%. That's what you get when 12.5% leaves from the 1 represents 100%, so you're taking 12.5% away from 100. Leaves you with this number. Why is that decay? Because that number is less than 1, so it does represent decay. And this is the initial amount. Remember, A stands for the initial amount, so that is how much is originally in somebody's cup of coffee. I guess they say tea or coffee, green tea. So if you graph it, it looks like this right here. It says estimate the amount of caffeine in a teenager's body 3 hours after drinking that tea. So we take that number, and that stands for time. We plug in 3 right there. And here's an easy way to do it. On the calculator, you can obviously just plug that in, or you can go like this. You can type in that equation, 35 parentheses 0.875 to the x power. And then we'll go to second table, and we want 3 hours after. So 3 hours after, there's the number. 23 milligrams would be left. So that's section 7.1 on graphing exponential functions.